Okay, welcome back to the Algebra 2 final exam review. In this video, we're going to still cover section 13, but we're going to start with number 181. So we have a different type of problem than we had in the first part of this section. And this one is when we're trying to simplify square roots or cube roots. So we have a handful of those in here as well. But we're trying to simplify radicals with variables inside of them. So for this first one, for 181, we have the square root of 256 times the square root, times a squared. So anytime we're doing problems like this, and we have variables involved, we want to break this up into the square root of 256 times the square root of a squared. So we want to separate our numbers and our variables. So then we just want to evaluate these things individually. So the square root of 256, if you look at your chart, you'll see that this is actually just 16. So we didn't need to make a factor tree here because 256 is a perfect square. On the other hand, what about this square root of a squared? Well, remember this is an index of 2 right here. And the best way to simplify these is to ask yourself, well, how many times does 2 go into 2? And 2 goes into 2 once with no remainder. So this is going to be times a implicitly to the first. And we don't even need to write that first power there. We can just write this as a, and then we're done. 2 goes into 2 once, so we have a to the first power, a to the power of 1, because it goes in once. And multiplying these two together, we say that this is 16a. And this is our final answer. Something that I want to share real quick is, what if we did have a remainder? What if we had, say, the square root of a to the, not to the fifth. What if we had square root of a to the third? Well, again, we have a implicit index of 2 here, and we ask ourselves, well, how many times does 2 go into 3? Well, it goes in once with a remainder of 2. So a to the first, because 2 goes into 3 once, times the square root of a to the power of whatever our remainder is. So 2 goes into 3 once with a remainder of 1. With a remainder of 1, this is a to the first as well in here. And simplifying that, we would have a times the square root of a. And this actually works for whatever index we have. So what if we had, say, the cube root of a to the fifth power? Well, we ask ourselves, how many times does 3 go into 5? It goes in once, so we just have a to the first, times the cube root of a to the power of whatever our remainder is. So 3 goes into 5 once with a remainder of 2. So we would say it's a times the cube root of a squared. So this number right here, this exponent, implicitly we had 1, is how many times this number goes into this number, whole number of times. And then whatever your remainder is going to be inside the root still. So with this in mind, we can now tackle the rest of our problems that we have here. So for number 182, we have the cube root of 40 times v. So even though we're doing cube roots, we still want to split this up as the cube root of 40 times the cube root of v. And kind of like how we simplify square roots where we divide by perfect squares, since we're taking the cube root, we want to divide by perfect cubes. So remember, cube roots, perfect cubes, we have the cube root of 8 is equal to 2. the cube root of 27 is equal to 3. The cube root of 64 is equal to 4. Cube root of 125 is equal to 5. Clearly, perfect cubes are a lot larger than perfect squares. They grow really quickly. And so if we're trying to simplify this, the cube root of 40, really we only have to check between 8 and 27, and the biggest number that's evenly divisible by is 8. So we can break this up as the cube root of 8 times the cube root of 5, and the cube root of 8 is 2. So this is a 2 here. And so we have 2 times the cube root of 5. I put a dot there so that it's not confusing if that's a 2 cubed. So I'll put a dot to separate our index from if we have an exponent over here. But I think I'm just going to do that for all of them, regardless if it has an exponent here. And then implicitly for this one over here, this is v to the power of 1. And so just like above, we would ask ourselves, well, how many times does 3 go into 1? Well, 3 doesn't go into 1. So it's already simplified. We don't have to do anything with that. We can just bring it straight down, and we have the cube root of v. And so what we can do is now we just want to simplify our answer by multiplying everything back together. So we want to take all the stuff that's outside of the root, so in this case it's just a 2, and multiply it together and put it on the outside in front. Then we take all the stuff that's inside cube root, or so inside cube roots. So we have this 5, and we have this v, and we just do 5 times v. So we have the cube root, put a dot there, of 5v. And so our final answer is 2 times the cube root of 5v. Let's try out number 183. For number 183, we have the square root of 75 into the 4th. And first, we want to separate this as the square root of 75 times the square root of n to the 4th. Next, we ask ourselves, what is the biggest perfect square that 75 is divisible by? And that number happens to be 25. So we have the square root of 25 times the square root of 3. Well, the square root of 25 is 5. And so down here we get a 5 square root of 3. And over here, we ask ourselves, again, this is an implicit 2 for our index. How many times does 2 go into 4? Well, 2 goes into 4 twice. So that's going to be n squared. But we don't have a remainder. And when we don't have a remainder, we don't have to put, I guess you could put times square root of n to the 0th power, but we don't need to do that because anything to the 0th power is 1. And so the square root of something to the 0th power is the square root of 1, but the square root of 1 is 1. So really, this is just a 1 here. And so we don't need to write it at all. So when your index goes into your exponent an even number of times with no remainder, you don't have times the root of anything. It's just 2 goes into 4 2 times, so it's n squared. Now we just need to simplify our answer. So we have 2 things outside of our root. We have a 5 and an n squared. So we take those and we multiply them together. We have 5n squared. And then the stuff on the inside of the square root is a 3. So we have times the square root of 3. And to make it clear for our final answer, times the square root of 3. Separate this with our dot so that 2 doesn't get confused for an index. So we have 5n squared times the square root of 3. Let's try out 184. So for 184, we have the cube root of 24 times p to the 7th. So first we separate this out. We have the cube root of 24 times the cube root of p to the 7th. Remember, our perfect cubes, we have 8, we have 27. So the only number that we need to check is 24 divisible by 8? And it is. We have the cube root of 8 times the cube root of 3. And the cube root of 8 is 2. So we have 2 times the cube root of 3. And over here, we're going to ask ourselves, how many times does 3 go into 7? Well, 3 times 2 is 6. And so this is going to be times p squared, because 3 goes into 7 twice, times the cube root of p to the power of whatever our remainder is. So 3 goes into 7 twice with a remainder of 1. So really, we have a p to the 1 over here. However, we don't need to write that 1 there. It's just cube root of p. And now we multiply all of our stuff back together. We have a 2 right here and a p squared right here. So we have 2p squared. And then times the cube root of all the stuff inside of our cube roots. So we have a 3 right here and a p right there. So the cube root of 3p. And that's our final answer. Let's look at 185. So for 185, we have the cube root of 48 x to the 4th, y to the 4th. So just like before, we separate everything out. We have the cube root of 48, the cube root of x to the 4th, and the cube root of y to the 4th. We ask ourselves, is 48 divisible by a perfect cube? And it is. It's divisible by 8. So we have the cube root of 8 and the cube root of 6. Well, the cube root of 8 is 2. So down here, we're going to get 2 times the cube root of 6. Then we ask ourselves, how many times does 3 go into 4? Well, 3 goes into 4 once. So we have x times the cube root of x to the power of whatever the remainder is. Well, 3 goes into 4 once with a remainder of 1. So we would write a 1 right here, but we don't need it. So it's just x times the cube root of x. And the same thing over here. Well, this is just now with y. How many times does 3 go into 4 once with the remainder of 1? We can write that as y times the cube root of y. Now we want to multiply all of our stuff outside of the root. We have a 2, we have an x, and we have a y. And so we have 2xy on the outside. On the inside, we have the 6, the x, and the y. And when we multiply all of those together, we have times the cube root of 6xy. So there we go. And this is our final answer. Let's look at number 186. We have the square root of 100 a squared b cubed. So let's separate this out as the square root of 100 times the square root of a squared times the square root of b cubed. Well, the square root of 100 is just 10. So That was nice. No factor tree required. We implicitly have 2's for our indices here. And we ask ourselves, well, how many times does 2 go into 2? And it goes in once with no remainder. So this is just times a. It's implicitly to the power of 1 because 2 goes into 2 once. We then ask ourselves, how many times does 2 go into 3? Well, it goes in once, so we have b to the power of 1, times the square root of b to the power of whatever our remainder is. Well, 2 goes into 3 once with a remainder of 1, so this is just b to the power of 1 in here. And so, gathering up all the stuff that's outside of our square roots, everything's actually already in order. We have 10a and b, so 10ab, and then times the only thing in a root, which is the square root of b. And so this is our final answer. Let's look at number 187. For number 187, we have the square root of 63 m to the 4th m squared. We separate this as the square root of 63 times the square root of m to the 4th times the square root of n squared. We ask ourselves, what's the biggest perfect square we can divide 63 by? Well, that number is 9, and 9 times 7 is 63. Well, the square root of 9 is 3. So we have 3 square root of 7. And we implicitly have indices of 2 here, so we ask ourselves, how many times does 2 go into 4? It goes in twice with no remainder. So this is m squared. And then we ask ourselves, how many times does 2 go into 2? Well, it goes in once with no remainder. So we just get an m squared and an n. All the stuff on the outside of the root, we're going to multiply together. We have 3 m squared n, and then times whatever is on the inside of the root. In this case, it's only a square root of 7, so square root of 7. And this is our final answer. So for 188, we have the square root of 16uv squared. And we can break that up as the square root of 16 times the square root of u times the square root of v squared. Well, the square root of 16 is a perfect square already, so this is just 4. And the square root of u, well, this is implicitly a 2 here, and there's implicitly a 1 here. We ask ourselves, well, how many times does 2 go into 1? It doesn't. So this is already simplified, and it's just the square root of u. However, we do have an implicit index of 2 here, and 2 goes into 2 once, with no remainder, so it's just v to the power of 1. And since we have no remainder, we don't have anything to, a root to put next to it. So all the stuff on the outside of the root, we have a 4 and a v, so we have 4v. And then the stuff on the inside of the root, we have just this u. So we have 4v times the square root of u. And now for our last 4. So our last 4 have 3 variables each, but it doesn't get any harder. We have the square root of 48 times p squared times q times r squared. We break this up as the square root of 48 times the square root of p squared times the square root of q times the square root of r squared. Next, we ask ourselves, is 48 divisible by, well, what's the largest perfect square that 48 is divisible by? And it's actually by 16. So 16 times 3 is equal to 48. And the square root of 16 is 4. So we get 4 square root of 3. And now we have our implicit indices of 2 here. How many times does 2 go into 2? It goes in once with no remainder. So we just have p to the power of 1, which is just p. We then ask ourselves, how many times, we have an implicit exponent of 1 there, how many times does 2 go into 1? It doesn't. So this is already simplified. It's just the square root of q. And then similarly, we have how many times does 2 go into 2? It goes in once. So we have r to the power of 1. We gather up all of our stuff that's outside of a square root. We have a 4, a p, and an r. So we have 4p r. And now we gather up all the stuff that's inside the square root. We have this 3 and the q. So we have square root of 3q. And this is our final answer. Next, we have for 190 the cube root of 108 p to the 8th, q to the 5th, and r to the 3rd. So first we separate this out. We have the cube root of 108 times the cube root of p to the 8th times the cube root of q to the 5th times the cube root of r cubed. And we ask ourselves, what's the biggest perfect cube that 108 is divisible by? So you'll have to check your chart, and after a little bit of introspection there, you'll see that that is the cube root of 27. So 27 times 4 is equal to 108, and the cube root of 27 is 3. So that means we have 3 times the cube root of 4. We ask ourselves, how many times does 3 go into 8? And it goes in twice, so we have p squared with a remainder of 2, so times the cube root of p to the power of 2. Next, we have how many times does 3 go into 5? Well, 3 goes into 5 once, so we have q to the first power times the cube root of q to the power of 2, because 3 goes into 5 once with a remainder of 2. And lastly, we have how many times does 3 go into 3? It goes in once with no remainder, so this is an r. And I ran out of room on the bottom of my page here, so I'm going to write it above. But we have 3 p squared, q, and r outside of our root. So we have 3 p squared. Getting a phone call. Hello. Okay. Okay, so resuming. We have 3 p squared times q times r. And then the stuff on the inside of the root, we have a 4, a p squared, and a q squared. So this is times the cube root of 4p squared q squared. A lot going on here, but this is our final answer. All right, we have 2 more. So for this next one, we have 191. This is the cube root of negative 625 p to the fifth times q times r to the seventh. So we break it up. Something to note is that when we take the cube root of any odd numbered root of a negative number, that we just bring the negative outside. So in this case, the cube root of negative 625 is just equal to negative cube root of 625. So we'll keep that in mind. We know that our answer has to be negative because of that, because bringing out this negative here. But we can break this up as negative cube root of 625 times the cube root of p to the fifth times the cube root of q times the cube root of r to the seventh. So dividing 625 by the biggest perfect cube we can find, that would be the cube root of 125 and the cube root of 5. Well, the cube root of 125 is just 5. So we have negative 5 times the cube root of 5. We ask ourselves, how many times does 3 go into 5? It goes in once with a remainder of 2. So we have p to the first with a remainder of 2, so p to the second inside of our cube root. 3 doesn't go into 1 at all, so this is just a cube root of q. And 3 goes into 7 twice with a remainder of 1. So we have r squared, because 3 goes into 7 twice, times the cube root of r to whatever our remainder is. Our remainder would be 1. And so we don't really need to write that 1 there. But now, we just have to simplify everything. So all the stuff on the outside of the root, we have a negative 5, a p, and an r squared. Multiplying all that together, we get negative 5p r squared. And then multiplying all the stuff on the inside of the root, we have a 5p squared r. This is going to be times the cube root of 5p squared times r. Oh, and a q. Sorry, forgot about the q there. Easy fix. So 5p squared r squared. 5p squared q times r. There we go. And that is our final answer. And for the last one, we have the cube root of 192. So no, it's not the cube root of 192. The problem is 192. It's the cube root of negative 256 x to the 8th, y to the 7th, z to the 6th. So again, we split this up. So it's the cube root. Remember, we can take out that negative, so this is negative cube root of 256. And shorten that line a little bit. Times the cube root of x to the 8th, times the cube root of y to the 7th, times the cube root of z to the 6th. So 256, biggest perfect cube that's divisible by. Again, you consult your chart to figure that out. And you'll have a calculator on your exam, so it shouldn't be that hard to do. But you're probably not going to have numbers this big on your exam anyways. But the biggest number that 256 is divisible by, that's a perfect cube, is 64. So the cube root of 64 times the cube root of 4. Well, the cube root of 64 is 4. So we're going to have negative 4 times the cube root of 4. And then we ask ourselves, how many times does 3 go into 8? 3 goes into 8 twice, with a remainder of 2. Then we ask ourselves, how many times does 3 go into 7? 3 goes into 7 twice, so y squared times the cube root of y to whatever the remainder is. The remainder of 3 going into 7 is twice with a remainder of 1, so just cube root of y. And then we ask ourselves, how many times does 3 go into 6? Well, it goes in twice with no remainder, so it's just z squared. We multiply all of our stuff outside of a root. We have this negative 4, an x squared, a y squared, and a z squared. So we have negative 4, x squared, y squared, z squared, times the cube root of everything on the inside of the root symbols. So we have 4, x squared, and y. 4, x squared, and y. And this is our final answer. So that's all I have for this video. And thank you for watching.